All right, so dynamics, introduction. So you got the syllabus. And I can assure you it's as exciting as all syllabi are. Okay, I'm David Kidd. My office is over there. Got my email there. Now we're going to, I save this stuff and it's just, okay. We got some errors here. Sorry. But they didn't save. So here we go. So the class time, let's see, office hours are Tuesday, Thursday, and this should be right on the printed syllabus anyway, 10:30 to 12:30. And the room time, and well, we're gonna be in here every day of the week from 1 to 2 basically. Okay, so that's where we'll start with that. So we're going to start with that, okay? Now, what else do we got in here? All right, now what we're going to do in here is we're going to take some kinematic equations, like motion equations. If you've had physics 1, you probably covered those, which would be a good thing. We're going to add the stuff we learned in statics to it, because we're going to go a bit beyond physics. Physics, I think mostly you deal with little particles and such. We're going to deal with larger objects that spin and rotate and do all that sort of thing. We're also going to work with work energy and impulse momentum, okay? And we're going to do this stuff both for particles, I think, as you do in physics, but also for objects that have dimension and different parts and shapes and that sort of thing. So we'll go a little bit more in depth, perhaps, than you did in physics, and we'll also apply some of the concepts that we used in statics. So to be in here, you should have had statics. You should be able to integrate, okay, like doing integral calculus, okay? And it's good if you've had physics before you come here. It's not absolutely required, but it's good preparation. Kind of the basics of what we do is covered in physics. Okay, so we're good with that. All right. Now the textbook is really a set of notes. It's called the Dynamics Notes. Be sure you have the second edition there, which is the one if you went to the bookstore to get them, you have that. You should also have a dynamics text of some type. It really doesn't matter which one. I mean, the homework is covered in the notes, so you could use any dynamics book you liked that you could find. I like the Hibbler one because it reads, of all the ones, how they're written, to me it reads the best, okay? But, anyone would be fine. Now, let's see. All right, now if you don't have the packet here, which you need, or the notes, they're in Moodle also, okay? So for those of you online, you can go into Moodle under the downloads, and there's notes downloads and homework downloads that'll keep you, keep you going here for a little bit, but you do have to eventually get the packet. So it's available down at the bookstore. I think you can order them online too if you want. So be sure you have the thing. If you don't, it's really tough to keep up with the class. The homework's in the packet too, so you just can't really do the class without some form of the packet. So don't try to do that, okay? Just be sure you get one. I don't know, 15, 20 bucks. Okay, now I did make a pretty significant change, but it was quite a few years ago. So, just be sure you got the right rocket ship on the front. So you got the skinny tall one as opposed to the one on the right. So, just be sure you got the second edition, and the cover has a photo on it that looks like that, okay? And you should. I can't imagine that you wouldn't, okay? Because
talking about the notes or the textbook?
The notes.
Oh, okay. Yeah, I got it.
Okay. All right. So just be sure to get the notes here, okay? All right. Now, we do grades here, of course. I use 2 systems. I use the first system. I count each exam equally. There's 2 midterms and a final. The homework's always 15%. System 1, I count each of the tests equally. System 2, I weight the final more. I use both systems, and then whichever system gives you the best score, that's how I issue the grade. The grade's just on a straight percentage, okay? So that's how that works. So just be aware that I use two systems. I have a little grader spreadsheet in Moodle. If you ever want to download it, you can check and see where your grade's at if you're ever curious about that, okay? Now, I can't do this in Moodle. It's not sophisticated enough to do a logic routine here. I have to run the grades both ways and then do a little comparison and take the higher of the two and make that into your score. So Moodle just won't do this. So keep that in mind, that Moodle does not tell you what your grade is for the class. There's an automatic category in there that gives you a score for the class, but it's meaningless because it's not based on this formula, okay? The formula is calculated on a spreadsheet that I've got, and I've got a copy of it there if you want to get it, but you can't, the score, the overall course percentage in Moodle is meaningless. It doesn't mean anything. It's just an auto-generated category. I can't get rid of it, but it's a meaningless thing, so just be aware of that, okay? Everybody good with that business there? Okay. All right, now the exams, people like to know when the exams are. Midterm 1, usually week 4, later in week 4, midterm 2, week 8. I'll give you at least a week's notice for the midterms. I don't have a specific day scheduled as many instructors do. I don't do that, so just be aware of that there isn't like a specific day scheduled yet, but the first one should be week 4, usually towards the end. The second one will be week 8. I'll give you a week's notice, so you should be good with that. Okay, the final exam is, again, I had this thing fixed, but anyway, that's neither here nor there. It's Tuesday from 2:30 to 4:30. And, I can't remember the date. I think it's March 20 is what I think. That's right. March 20. Okay, thank you. So that's March 20. Okay. There we go. Okay, so that's when the final will be. Now, that's off the normal time. I schedule it on our Tuesday class time, so just be aware of that. We'll cover that when we get to the end of the term, too. I do that because if you take kind of the typical curriculum at the typical time, you end up having a bunch of exams on Monday. So I've changed when our exam is offered. Okay, on the back of the syllabus, I've got some stuff, what employers expect of an employee. Pretty good list, for school too, so I just put it on there. I kind of like that list. Okay, I've got disability services and emergency planning. I've got an anti-discrimination statement. So the disability services, emergency planning, if you need some sort of accommodations, just let me know and we'll work them out. No worries there, just communicate with me and we'll work that out. Anti-discrimination statement means basically treat people good, I think, even if they're different than you, all right? And we got quite a list of differences there, but just treat people well and with respect, and I think we'll be fine. I've also got a thing on academic honesty, okay? And basically what that says, you can read through that, but it says that no copying or cheating, okay, is what my academic honesty thing says. And if you are academically dishonest, which means you're copying someone, which is a form of cheating, or other, I guess, or doing any sort of cheating, you get a 0, okay, for whatever it is you're doing. Now, if that happens on a midterm, you can't ask the class to get a 0 on a midterm. So just please don't do anything dishonest on this stuff, especially on a midterm, okay? Now, if you're helping someone cheat, that's academic dishonesty, okay? So realize that too, okay? So just be careful about this, show respect for me and and for this institution here. Okay, so just be aware of that's not something I can tolerate. It just destroys the whole fabric of the class. Okay, if people are doing that, and I just can't tolerate it. So just be aware of that. Okay. Okay. What else do we got here? All right, so any questions on the syllabus there? We're doing okay? Now I require a certain format on the homework. You know, it's the exact same as what I did in statics. Does anybody need a copy of this? Anybody else? Okay. All right. Now, the deal with this is it's not only important that you can do the work, it's also important that someone else can follow what you're doing, okay? That's the idea. It's also important that who's ever following it has some confidence in what you're doing. So those are the basic ideas behind this, okay? So, you know, and you'll find that I think when you go to work, people are going to have expectations of the work that you're doing. All right, so what we want to do, we want to keep it neat and organized and legible. One, that allows people to read it. And two, it makes it look like a professional did it. So I use a straight edge, okay, when I do this. Create work that can be followed by somebody else, all right? So that's important because people need to look at your work and figure out what the heck you're doing, okay? It isn't just you're doing it, you're showing someone else how it was done. That's the idea, okay? You know, that's something that always drives me a little crazy when I'm grading tests too. People don't quite understand that sometimes. Show work that I can follow. If you do that, I can grade it. If you fail to do that, boy, you really put a lot of you're put a lot on my plate when I can't follow it. You're kind of relying on me. Then you shouldn't do that. You should be taking care of yourself and laying out that work so I can follow what you're doing. Okay. Use arrows to show the directions of forces and moments. Put all the answers to one problem in a box. One problem per page. Draw your own sketches just to get, you know, use a straight edge. Get a decent sketch in there. Do it quick. Don't waste time. Show units in your answer. Okay. So that's the idea on this stuff. Okay. So let's see. There you go. So there's an example from statics. Name, date, problem number, page number on the top. You know, I didn't write the whole problem statement down. I just paraphrased it. I don't want to waste time writing the whole paragraph down. Find the forces at the supports. Got a sketch there, simple line sketch with a free body diagram. Got to use a straight edge. Work through the problem in a way somebody could follow and boxed in the answers. Okay, that's basically it. And as I've said, when I went to work, man, I got a lot of grief about how my work was when I started. One guy in particular used to write me pretty badly about it, so I really suggest that you learn how to do it quick and neat now instead of waiting to go to work. That's my suggestion anyway. These are our ones that I see. Excuse me, I guess I'm not. Okay, there's the formula sheet, okay? It's a little bigger than the statics one, isn't it? So it's got a few more formulas. We'll spend some more time going through this, okay? Basically, the front is the dynamics formulas arranged by topic there. And then the back just has properties of different shapes. And then I'll also point out that the back also has a few things on there that you might want to know sometime. These are the things that over the years, in the middle of a test, people have this very sheepish look on their face and they walk up to me and they say, I can't remember the quadratic formula or something like that. And I don't really care, so I put it on the back, okay? I can't remember how to convert degrees into radians. Okay, that's on the back. I can't remember what G is for Earth. I put that on the back. Okay, it's on the back, any of that stuff, okay? So just realize it's there. All right, so this is just for your general reference. You also get it during a test, okay? So this is what you get on a test, is this sheet. It's available online for those of you in Moodle that are taking the class online too. All right, and then this is the same stuff that if you took statics, I had this up. What have you learned this year at Oregon State University? This is pretty classic. Showing up for class is pretty important. It is important, okay? Show up, engage, okay? That's important. Houston, we have a math problem. This is when they crashed a Mars rover into Mars because the design team, I think they used metric units and the operations team thought they were using English units, and they screwed up and just smashed the thing into Mars and it broke and wasn't any good after that. So just carry your units through, work slowly through a problem. It'll save time in the long run if you set them up properly and work through them systematically, okay? And this is Teen Beach Movie, the two leads. The smart one who's Mac says to the more, shall we say, intuitive one, Brady, I can explain it to you, but I can't understand it for you, okay? Right? So my job is to explain. That's what I do. But you got to understand. And just listening to me explain doesn't mean you understand yet. You got to do the work on your own. You got to understand it yourself, okay? And, I'll show you how to do stuff, but you got to learn how to do it, okay? Those are different things. Okay. There we go with that. So we got any questions on that bit? Okay, all right. All right. Well, we're just running right through this stuff, aren't we? All right, let's have a look at just a little bit of dynamics here. We got a couple minutes, so let's have a look and see what we can do. If I can get this dang thing to work. Here we go. Dynamics. Okay, so this is either on page 110 of your packet. Now, if you got the notes or the packet or whatever you want to call it, the first 30-some pages are numbered 1, 2, 3, 4, 5, up to 32 or 4 or something like that. And those are the homework problems, okay? That's what I'll pick from those to assign homework. After that, I've got the notes. Now the notes, I start numbering them on a page 110 and I number them by tens. That way, if I want to add pages, I can do it. I've got open numbers I can put on the new pages, okay? So that's why it's numbered that way. It is a little bit uneven in how it's numbered, but it's sequential. So, 120 is after 110, okay? Okay. So now this is why you want to bring the notes every day, because I've got stuff in there, or this is one reason anyway, I've got stuff in there that you don't want to be copying down. I don't want you to copy it down. It's a waste of time. I just want to cover it real quick and I put it in the notes for you, okay? So it's just much more efficient to have the notes than it is to try to copy all this stuff down. All right, so dynamics is motion, and particularly accelerated motion. So in statics, the sum of forces is 0. That's an assumption in statics. In dynamics, it's not. So things get a little bit more complex. And that's why things accelerate, because the sum of forces is not 0. We look at kinematics, which looks at the geometry of motion, how things are moving. We start there, and after that we go to kinetics, which looks at what causes the motion in the first place. Okay, so the first part of the class, we're just looking at motion. Then we look at what causes motion. Okay. A particle is a point mass. It really doesn't matter so much what the size is. You can consider the Earth to be a point mass if you're analyzing the solar system. Okay. But you could consider a point mass to be a pool ball or an electron on an atom, or who knows. But it's just all you're doing with a particle is just looking at an object like it's a dot. It has no dimensions. Okay. Rectilinear means kind of a straight line. Okay, and then we get into the variables we use. Position is location with respect to the origin. R is the position vector. Notice that R is bolded. If you're going to write down R as a position vector, you'll put an arrow on top to show it's a vector. Okay, if I'm typing it, I'll bold it. Okay, S for some reason is the position scalar. So they change the letter when they go from the vector to the scalar. I'm not quite sure why, but they do. Okay, now what we call displacement is a change in position. So delta R is your final position, R2, minus the initial position, R1. Okay, and then you got delta S is S2 minus S1. Distance is the total length traveled. Distance is always positive. Distance is always greater than or equal to displacement. Okay? So, if you start there at 1, and then you go to 2, but let's say to get from 1 to 2, you go 1 block east and then a block north as you're walking, let's say. Your distance is 2 blocks. But the displacement is not. The displacement is the straight line that connects 1 to 2, which in this case, using the theorem of Pythagoras, would be what? 1 squared plus 1 squared, which is the square root of 2. But of course, being as I'm an engineer, I'd never write down an answer like the square root of 2, because I know that a machinist wouldn't like that at all. Okay, so I'll give them a decimal. Okay, so that would be 1.414. Okay. So that's the difference there between displacement and distance, okay? They mean different things. They're related things, but they're different. Okay? We good with that? Okay. Okay. Now what we got next here is kind of a chain of related things. So T is this time. That's a scalar, okay? Unless you're doing relativistic physics or something, I think, but we're not. So it's a scalar. R and S are displacement, which is how far you go. V and V are velocity, which is the displacement over the time. It's the speed you're traveling at. If you're driving, it's your speedometer reading. 45 miles per hour, okay? A is acceleration, which is how much the rate at which your velocity changes. So if you're driving down the road going to Corvallis and you pull out on 34, if you step on the gas, your body will kind of swing back into your seat, right? You're changing the velocity, you're accelerating. If you step on the brakes, you'll kind of lurch forward. You're accelerating again. That's acceleration. Now these things are related. All right. So V is dr dt. So velocity is the change in displacement with respect to time. So you talk about velocity in foot per second. Displacement over time. Now we do a lot of time derivatives in this class. So instead of writing out dr dt, normally we just put a dot over the letter, and that means a time derivative. Not any derivative, but a time derivative. Okay. So we can talk about dr dt as a vector or ds dt as a scalar. We can also look at average velocity too, which wouldn't be instantaneous. That would be looked at over a given time interval. Now, acceleration is the change in velocity with respect to time. dv dt. Okay, now that's v dot. Now being as v is s dot or r dot, the acceleration is r dot dot, meaning a second time derivative. Okay, so those dots just mean time derivatives is all they mean. Okay. So those are the fundamental definitions. V is the change in displacement with respect to time. A is the change of velocity with respect to time. So you can play around with those kind of like they're algebraic variables. And you can solve them both for ds, or excuse me, for dt, the change in time. So the change in time is the change in displacement divided by the velocity. Using the right-hand equation here, the change in time is the change in velocity over the acceleration. You can then set ds over v equal to dv over a, cross multiply to solve, and get a third relationship that doesn't involve time. AdS is vdv. So the acceleration times that instantaneous change in displacement is velocity times the instantaneous change in velocity. Okay, so those are three fundamental calculus relationships. They're in the upper left-hand corner of the formula sheet because they're important. All right. You doing all right with that? A little bit of information there, but that's kind of the deal. Okay. That wasn't supposed to happen. All right. Edit. Come on now. I'm going to edit. Edit. Undo. No, you don't like that, huh? Okay. Undo. What's that? Oh yeah, probably go there. I don't have my mouse here today. Full screen, no. Fit to width. I will just go full screen. Let's try that. Thank you. That's probably a good idea. Thanks. There we go. All right. Now, a lot of times we got constant acceleration. Now, if we got that, we can simplify these calculus relationships down into algebra relationships. Now, these are just derivations. These equations here are just, they're on your formula sheet too. Now, I didn't include this in the stapled handout because they're just derivations. They're in the packet, okay? So if I have a equals dv dt, that means that a times dt is dv, and I can integrate that out to solve it, and I could work it down to this equation right here. This holds for constant acceleration right here. These three equations. So they're the constant acceleration versions of the calculus relationships we just derived. Now, sometimes you do have constant acceleration. What's probably the most common example of constant acceleration, do you think? Gravity. Yeah, I think gravity is, okay. So we use that. That's a sub c quite often if an object is falling. Okay. Which is interesting because that gets us to this first little example we've got. So let's say we throw a ball upward at 22 meters per second and it's released 1.8 meters above the ground. How high will the ball go and when will it hit the ground? How fast will it be going when it hits the ground? Okay. So the first thing you want to look at here is, am I dealing with calculus or am I dealing with algebra? Calculus is for variable acceleration, algebra is for constant acceleration. So what's causing acceleration here is gravity, I think. So that's constant, eh? So we can do this algebraically. No reason to have to do this with calculus. So that's the first little point I'd hit on this, is that this is an algebra problem. And I'll use the three algebraic equations. Now the next thing I look at is what's the velocity at point B? It's zero because that thing's moving up right before B, right after B, it's moving down. There's that 1 second where it's turning around. Okay? So that has a zero velocity at B. Okay? So VB is zero. Y'all okay with that? You doing okay? All right. All right. Now, let's figure out how high the ball is going to go. Now, we're given that the ball leaves the thrower's hand at 22 meters per second, so I put that in there. It's being thrown up. So I put an arrow in there that goes up. And I want to figure out how high it's going to go. Now, I've decided it's going to be an algebraic equation. We've got 3 equations to use. So one thing to remember in dynamics is kind of narrow things down. I wouldn't be scratching my head here saying, what am I going to do on this? I'd write down the 3 equations and say, I got to use one of them. So, you know, there's only 3 choices. So how high will the ball go? That suggests a distance, doesn't it? So which equation should we use here to figure out how high it'll go, given what we know?
Can you find the time it takes to reach a velocity of 0?
Yeah, that's a good point. There's different ways to do this. I mean, you could find the time and then use the time, or you could just use that displacement equation too. And there's more than one way to do these. On this one, I just went ahead with the equation on the right, okay? Because I don't have any information about time yet. So to figure out directly how high it would go, I used the equation on the right. Now, let's see, can I escape out of there? Will that work? Maybe, okay. Now, when I'll go back, but okay, so I use the equation on the right because it has velocity, which I've got the starting and ending velocity, and I've got the acceleration. So that's enough, you know, that's enough for me to solve this thing out, the one using the equation on the right. Now, the important thing to realize here, one of maybe many important things, is the acceleration is down. So when you're doing this stuff, you gotta get things going the proper direction and having the proper sign. So I know the final velocity is 0. I know that. And I also know that the initial velocity is 22. And then I've got 2 times the acceleration. Well, that has to be negative. Okay. And then I've got S, which is the height. But notice the height is measured from the ground. The ball is released 1.8 meters up from the ground. So to get I'm going to take that height, and then to get this distance here that I'm solving for with using the velocity of 22 and 0, I'm going to use S minus 1.8. So these equations are simple enough to use, but there are some finer points on how you plug things into these things. You got to pick up the fact that your final velocity is 0. Get that on the left-hand side of the equation. Your initial velocity is 22. Get that on the right-hand side. The acceleration is down, so that's a negative 9.81. And the height, as it's defined there, would be the S distance, which is S, is 1.8 meters more than what we're solving for. So we got to find the height. We got to take S minus 1.8. Okay? And then we work through the numbers and we get S is 26.5 meters. Everybody okay with some of the finer points on that? Now, you could have solved for time first and then backed into the distance. I mean, you know, there's different ways to put these things together. It's not a big issue. I mean, whatever will work for you is fine. Okay. But you just kind of look for the proper equation to solve for what you want to know. That's how I think about these. Once I identify that this is a constant acceleration equation, then I know it's an algebraic equation. And once I know that, I know I got 3 equations I can work with, okay? So that's kind of my thinking on this, okay? Now, if I want to know when it'll hit the ground, we got time for just one more thing on this. So when will it hit the ground? Okay, again, I've got an equation to use. I want to know when, so I'm looking for time. Now, what I've got there is the initial velocity and distance. I've got the final distance. I've got the acceleration. I think I'll use that middle equation. Now, sometimes I've seen people in a situation like this want to use this equation because when the thing hits the ground, the final velocity is 0, right? But you can't do that because the reason the final velocity is 0 is there's the ground there and it hits the ground and bounces. This equation does not account for the fact there's the ground. It's just looking at the effects of gravity on the object. So you can't assume the final velocity is 0 and use these equations because they're not sophisticated enough to know that there's the grounds there. They just run the motion due to the gravitational effect. Okay, that's all they do. So you can't assume the final velocity is 0 because what you're really looking at is the velocity of the object right before it hits the ground, not after. And again, those equations do not account for the fact that the ground is where it is. Okay, so we're going to go S is S0 plus V0t plus 1/2 ACT squared. Plug everything in there. S is 0. S0 is 1.8 because the ball's released 1.8 meters above the ground. V0 is 22. A is negative 9.81. Can run through the numbers. You're going to have to use the quadratic equation and solve for t, negative 0.8 and 4.57. Okay, and you're going to use the positive result because we're not going to go back before time 0. So there's another example of the limits of the equation. The equation's just running this parabolic path. It goes into negative time and it does all sorts of things that aren't really happening here. Okay, so that started at time 0 and kept on going. If you plug a negative 0.8 seconds into the equation, you'll get that position right there on the ground on the left, see? But that's not realistic. That's not what's happening here. We're throwing the ball up and it's coming back down to C. So 4.57 seconds is what you'd want. Okay. Okay, why don't you do one of these for Wednesday because they're kind of fun. If you have the packet, it's problem 111. If you don't have the packet, I can hand you this thing here. So why don't you do that for Wednesday? We'll cover it tomorrow. Yeah, if you need a copy of this, they're online too. So just 111 for Wednesday. We'll go over it tomorrow if you got questions on it. Everybody got this? And 111's online too for those of you that are online. Okay, so we good? We'll call it good here. Okay, we're good. Escape. All right, so the homework here is 111. All right, so that's due this Wednesday. Okay. And that would be the 10th from the look of it. Okay. So there you go.